Listen to that. But behind that satisfying sizzle is a specific challenge of heat transfer that's surprisingly difficult to solve. Look at a quiet, room temperature piece of raw beef. To transform this into a perfect steak, you have to move energy through it in a way that nature actively resists. On the exterior, we trigger the Maillard reaction, where amino acids and sugars recombine into flavor compounds at 310 degrees. But if the interior reaches 310, proteins dry out. To keep it tender, the center cannot exceed 130 degrees. This is the central problem of the cook. You are applying 500 degrees of heat to the surface, but you have to stop that energy from conducting just half an inch inward and overcooking the core. Success starts with the variables of the meat itself. A marbled ribeye contains ribbons of fat that conduct heat more slowly than the water-heavy muscle of a lean sirloin. That fat acts as a built-in thermal buffer. Then we build the flavor profile. By using salt and crushed whole peppercorns before the meat hits the pan, we're providing the raw materials that will eventually fuse into the crust. When the steak hits the iron, it screams. But that sound isn't the meat browning, it's the sound of surface moisture being violently converted to steam. This chart shows the evaporation barrier. As long as there is liquid water on the surface, the temperature of the meat cannot rise above 212 degrees, the boiling point. This is why a bone-dry surface is a prerequisite. You have to boil away every drop of water before the surface temperature can finally break 212 degrees and enter the zone where the crust actually forms. There's a persistent myth that a steak should only be flipped once for a good sear, but thermodynamics suggests otherwise. Leaving the meat stationary on a hot surface allows heat to conduct steadily and deeply into the center, creating a wide band of overcooked meat before the outside is even brown. The solution is a kinetic one. Flip the steak every 30 seconds. By flipping frequently, you give each side a short burst of extreme heat, then pull it away. The ambient air cools the hot surface, stalling heat conduction into the center. This frequent movement is the mechanism that allows you to develop a dark, caramelized exterior while keeping the internal temperature strictly under control. When the internal temperature finally reaches 105 degrees, it's time to add the enhancers: butter, garlic, and thyme. In this stage, the butter is more than just a seasoning. It becomes a highly efficient liquid conductor of heat. As you tilt the pan and spoon the foaming fat over the meat, the hot liquid flows into the microscopic pits and valleys of the surface, essentially frying the crust into the uneven texture of the steak. The fat also acts as a solvent. It extracts the aromatic compounds from the garlic and herbs, infusing them directly into the Maillard crust as it finishes. Basting essentially uses liquid fat to accelerate the final stage of the crust, while simultaneously locking in those dissolved flavor compounds. You have to pull the steak off the heat when the core is still between 120 and 125 degrees, well below the final target. Once on the cutting board, carryover cooking begins. The intense thermal energy trapped in the outer layers continues to migrate toward the cooler center. This inward migration provides the final push, gently bringing the core to a stable 130 degrees. The result of navigating these variables is a dark, savory exterior that gives way to a uniform pink interior from edge to edge. A recipe is ultimately an exercise in managing thermodynamics. By understanding the tension between the crust and the center, you're no longer just following instructions, you're actively controlling the variables of the cook.